Alright, so now we're going to go past intervals of increasing, decreasing, and see what we can do with a second derivative. And so we have a few terms that we should get used to first. And our ultimate goal is to be finding intervals of concavity. And we do that just like we did with finding intervals of increasing, decreasing. So first, definition. If the graph of f lies above all of its tangents on AB, it's concave up. And it's going to look like this. Opens up, basically. If the graph of f lies below all of its tangents, then it's concave down, and that's going to look like that. It just basically opens down. Okay, so if we want to find the intervals of concavity, then first we have to find solutions to f double prime is equal to 0, or where f double prime doesn't exist but f does. So that should look familiar. That's basically what we did with critical numbers, only we did it with f prime, not f double prime. So anytime f double prime is equal to 0, those x values are going to be possible inflection points. Then we're going to break up the number line. With those solutions, same thing that we did before. And we're going to pick test points. If f double prime is positive, the function's concave up. If it's negative, then the function is concave down. So just so we can get an idea of what an inflection point actually is graphically, it's these points right here where the x's are. So where a function is going to change from concave up to concave down, or vice versa, those points where it changes concavity are going to be inflection points. Alright, so final inflection points and intervals of concavity. So if f is continuous at c and f changes concavity at c, then it is an inflection point. So it's not just going to be where the second derivative is 0, it's got to change concavity. Alright, so we're given 3x to the 4 minus 4x cubed minus 6x squared plus 12x plus 1. So we want to find the first and second derivative. And so when we do that, we end up with f double prime is equal to 12 times x minus 1 times 3x plus 1. Alright, so it's important that we factor this just so that we can actually see where the zeros are going to be. If we solve that, we get 1 and negative 1/3. So if we break up the number line at negative 1/3 and 1, now what we're going to do is just like we did before, is test f double prime in this case, and that's going to tell us about the graph of f. So our test point for the first interval, maybe we could choose negative 1. If we plug that into the function, the second derivative, we get a positive, and that tells us that we are concave up. Second test point, x equals 0. If we plug that into the second derivative, we get a negative. So we're concave down. X equals 2 for the next interval, and that is going to be positive. So we're concave up. So notice that at negative 1/3 it does change concavity, and at 1 also. So we can list the intervals of concavity: negative infinity to negative 1/3, union 1 to infinity, concave down negative 1/3 to 1, and we have two inflection points where x is equal to 1 and x is equal to negative 1/3. The next few problems are basically just a review of stuff that we went over in class. That is limits at infinity. So there isn't any audio on that part, but it basically just states a theorem and then goes over a few different examples, maybe just one or two if I remember correctly. So you can watch that if you'd like. It's just another thing that's going to help us graph the functions after this section.